Software Engineering Radio, episode 102, Relational Databases.
This is Software Engineering Radio, the podcast for professional developers, on the web at se-radio.net. SE Radio brings you relevant and detailed discussions and interviews on software engineering topics every 10 days. Thanks to our audience and the partners listed on our website for supporting the podcast.
Welcome listeners to another episode of Software Engineering Radio. My name is Bernd Kolb. Today on the microphone with me is Arno Hase. Hi Arno.
Hi everybody.
So our topic today are relational databases. Arno, why don't you explain in a brief overview what are relational databases?
Sure. Well, relational databases are basically big boxes in which you can store any kind of data in a transactional way. There's another episode on transactions which goes into all the details of what transactional storage means. But a relational database means you have one big container, you can put anything you want into the container, and you have queries to retrieve the data, to look at it. They're reliable, they're robust, they're scalable, they're highly available, and have all these nice non-functional properties that are so useful in today's enterprise world and embedded and wherever. So relational databases basically are places to store data.
Okay, and so why is that topic interesting for me or important for me as a developer or architect?
That is really a good question. I mean, databases are so present in most projects nowadays that many people feel they have an understanding of them. People think, I know what databases do. I know how to write select. I know how to write an insert. So why should I go deeper into relational databases? I know all about them. And actually, I think this is one of the problems that people tend to think they know about relational databases. Many applications are designed nowadays with databases as an afterthought. You design the application logic and you have object relational mapping, and then you sort of feel, okay, I can plug in any database and it's going to work. And basically, it is not going to work really well unless you understand how databases work internally, because you run into all kind of performance issues, scalability issues. And so I think it's a good idea for developers and especially architects to be familiar with the persistence layer, technology and languages, and not only the middle tier languages like Java or C# or whatever.
I guess we should mention in the overview that schema design and writing database applications is not scope of that episode, right?
Right, yeah, very good point. Schema design is stuff enough for an entire other episode, which we might or might not do at a later time. And also designing application as a whole, it's out of scope. This is really just about databases per se. That brings to my mind an anecdote I heard about Kent Beck, who said you should not start with a relational database per se. You should not say, before you know what the application should do, I need a relational database. You should consider the alternatives. In good extreme programming manner, start with the simplest possible thing, which usually is file storage, and then build on that if you need something added. This is sort of a weird approach. Oftentimes you do know that you need a relational database, but it illustrates that there are alternatives. I mean, you can always store data in files, or if it's read-only data, read data from files, which is often a good alternative, at least for some kinds of applications. And then there's other kinds of databases, like object-oriented databases or hierarchical databases. So relational databases are not the only solution. It's good to have the whole range of solutions in scope, but relational databases are the most widely used technologies to store data. And they're basically all over the place. You have them in huge applications that store many rows of data, large amounts, Amazon or eBay or whatever. But you also have them in very small settings. There are relational databases nowadays that are used in embedded devices. So you have a whole wide range of different technologies, of different products. The underlying technology of relational databases is the same. This brings another thing to my mind. Most database vendors want to say that their database is the best, the biggest, the whatever. So they all bring their own kinds of benchmarks. And MySQL, I think, has the largest installed base, which means the largest number of websites that uses MySQL, which is quite probable, quite likely, because they're used by many very small online shops and sites. Whereas DB2 or Oracle or maybe Microsoft SQL Server, I'm not up to date, and it's very hard to check anyway, say they have the largest amount of data or the largest number of rows or the largest amounts of money that are managed. So you have a wide range of ways to say I'm the biggest database vendor in the world. And so if you hear some kind of statistics that way, don't take them too seriously. You cannot check them anyway, and every vendor has his own way, his own statistics that lets him look good. Which brings me to a very important thing here. We're going to mention different products and different vendors, but we're not paid by any of them, and we're not going to say this is a good database or this is a bad database. So whatever we say about them, there are many different vendors, many different products, and we're not going to endorse any of them in a special way.
Before you mentioned embedded databases, and so maybe you can explain what is an embedded database.
What I was talking about is a database that is small enough to run in an embedded device, which basically means it has very small memory footprint and very small disk footprint, and has real-time characteristics, but probably will not scale very well, which makes it applicable for small devices, embedded devices.
Mm-hmm. And then there's another kind of databases which are known as in-memory databases. What are their specific characteristics?
Well, in-memory databases are sort of exotic in the overall landscape. They're mainly useful for testing purposes. There are certain databases that run entirely in memory and keep all the data in memory, which makes them very fast, and means that the database driver usually is the entire implementation of the database, which means you can start a database, put data into it in a test without much installation overhead, which makes them very useful for development, but usually not for production use.
Okay, so I guess that's all for the introduction. I think we can now start with the relational paradigm. So what is the relational paradigm?
Okay, relational databases. I mean, relational sort of sounds like mathematics, and it is actually. There is a whole mathematical theory behind it that all data is stored in relations, and everything is a relation, which is sort of nice, has an aesthetic feeling to it, but it all breaks down to relational databases means everything is a table with rows and columns. The language to deal with relational databases is SQL, structured query language. There used to be all kinds of products in the 80s with all the different languages and dialects, but it was standardized way back. It's standardized quite well. And this paradigm means all data is stored in rows and columns. It is accessed by retrieving rows and columns. Several tables can be joined together to make different tables with rows and columns, and everything is a row and column. The strength of this paradigm is that it's very simple. Everyone can understand it, and the image of putting data in a table is well known to many people. It's sort of, you can sketch it down on a whiteboard or a piece of paper. And storing data in tables and columns is so widely used nowadays that it sort of feels like it's the only way to store data. But there are other approaches, especially hierarchical data, which means you have one root element, and from that you have data that is contained in it. That's basically the XML way of storing data. XML is the modern technology that stores data in a hierarchical way. You have one root element and children. You have a tree, and you have all kinds of. You have a whole paradigm, a whole group of databases, hierarchical databases that were on vogue before relational databases came along in the 80s. They're still used sometimes. And you have object-oriented databases that are sort of an arbitrary graph. You have an object here, an object there, an object over there, and they have pointers all over the place, which makes them very different. But relational databases store things in tables and rows and columns, which means that there is no concept of a reference between different tables. You have a table with persons, you have a table with addresses, and they have something to do with each other because every address belongs to a person, but there's no pointer per se, but the way to match data is to use a join. You have a column in the person table that identifies the person, which is called a primary key, and you have a column in the address table which identifies an address, which is called the primary key of the address table. Then you have another column in the person table that holds a value that is also a primary key in the address table, and then you match those and say if the foreign key in one table matches the primary key in another table, those two should be matched together. That's called a join. There's special SQL syntax for that. There's inner joins, outer joins. We're going to go into those in a different episode on SQL. And but the key thing to remember here is you can navigate any way. You can start all over the place, and the query language means the whole contents of the database are one huge pool of data. In a way, like everything is in one big global variable, and everyone can access it. There's no starting point. You can start anywhere and move by joining all over the place, all through the data, which is the special thing about relational databases. It's different from all the other paradigms that are sort of that have explicit links or hierarchies. In relational databases, you can start anywhere and have any kinds of conditions and move all over the place in any way you like, which makes them very, very powerful for queries, for arbitrary queries. And some of the queries that are, or if you have queries that you use more frequently, you can store those queries in views, which is basically a table without explicit data storage. It's a select query that you store with a given name, and since the results of any select query are a table, views look like a table. You can access them directly. And there are optimizations behind those. They're called materialized views. Some vendors have them, which means that they actually cache the results of the query. And some databases even allow writing to views, which is special and useful in some cases. Again, everything is a table, and the self-similarity is one of the strengths of SQL. So these kind of queries that pull together data from all places of the database and retrieve them and make them available in the form of a table. This is sort of the basic meat of querying a relational database and storing data in rows and columns with using insert or update. But there's a wide range of syntax built on top of that, like inner selects. You can select data and have a temporary table that is used as part of the query somewhere else, and you can have report kind of thing like grouping data, adding things, retrieving the maximum, the minimum value.
Sorting data,
exactly. And there's a huge range of syntax in SQL. You have case statements, you have if, you have string concatenation. Really, really cool, powerful stuff. We're going to go into that in the SQL episode. But the key thing is everything is a table. So all this syntax, all these special things are built on tables and return tables. And as you may have noticed, I think the relational paradigm is a really, really beautiful paradigm. I love this paradigm because it's so simple and yet so extremely powerful. The select clauses, that is the queries in SQL, are a very expressive, side effect-free functional language for those of you who love to go into language theory. They're sort of self-contained, self-similar. It's the underlying concept is very, very simple. And the downside is, as with so many simple paradigms, the performance is intrinsically limited. You're free to move around all over the place, but since there are no explicit pointers, all kinds of lookups must be done by the database engine at runtime, which tends to make it slower. And there's the whole issue of indexes to deal with this, to give the to tell the database which kind of queries to prepare a cache that is maintained whenever data is changed, which makes the lookups faster. This is one of the things that is very important to understand in order to write well-performing and well-designed databases, which goes way beyond the object-oriented paradigm of the middle tier this is something that is in the persistence tier, and you really need to understand how the database works, how your product works, what kind of lookups your queries do, and then you can understand what kind of indexes can be used to tune this. And you need to balance this because creating an index, if you have an index, it means anytime you change the data in the tables, the index must be updated. So actually, an index can make the database slower. There are special columns. Well, first of all, every column has a data type. Of course, there are built-in data types. Basically, the built-in data types you have in any language, and you expect from modern languages, that is integer numbers of different precision. You have fixed point numbers of arbitrary of different precision. You have strings, and you have date and timestamp, and that's basically it. There is no Boolean value, no Boolean type, which means you have to emulate that using a number usually. And you have special types for storing huge amounts of data. They're called blobs, binary large objects, or CLOBs, character large objects. Strings in the database are limited in length, which means there's a maximum length, which is important for performance optimizations inside the database. But you can have arbitrary size objects, blobs and CLOBs. It's good to have them, but they have huge negative impact on the performance, so you tend to avoid them unless you need them, which is sort of true of most things. There's special columns. I mentioned them: primary keys and foreign keys. Primary keys means you need to have one or more columns to identify every row in a table. They must be unique in order to have this property of being able to provide a way to look up data. And there are identifiers. There are different philosophies there. One traditional approach was to use business values as identifiers. And this, well, for example, for books, you could use the ISBN number, or for employees, the employee number that is printed on their company ID card or whatever. So you can have primary keys that are represented in the real world, that are actually accessible, that are visible outside the database, that have a meaning outside the database. And, well, this is, or the social security number in the United States is a very popular primary key used for people.
So the thing is that the primary key has to be unique within one database table, right?
Yes, the primary key must be unique inside every database table. And this leads to a problem if you use business values as primary keys, because, for example, social security numbers, they are unique, yes, but in cases of identity theft, you may have to assign a different social security number to the same person. So one person can have two social security numbers at different times. Or ISBN numbers are supposed to be unique, but there are exotic cases when they are not unique. Or you might want to recycle company ID cards so that the person who left, so after one employee left the company, let's say after 2 years, you assign the same employee number to a different employee because you want to reuse the ID card. So using these kinds of externally visible values as primary keys is potentially problematic because it is very difficult to change primary key values of rows. So the preferred approach today, the modern approach, is, and has been for quite a while, to use synthetic primary keys. That is, to have an algorithm that calculates a unique value for every row that is added, and this ID is used internally only. It's not visible outside the database, so you can assign it, you can manage it, you can use it without anyone else caring, which means there are no external forces that lead to the problems that I just sketched.
So are there any special strategies to generate the primary keys?
Yeah, there are quite a few strategies out there. There is sequence numbers, which is a proprietary but widely used feature of different databases, which means the database provides a way to access automatically incremented numbers. There is the special case of an auto-increment column, which means the database increments or assigns a new primary key to any row that is inserted. Those are useful at first sight. They have the problem that the primary key of a newly inserted row is just inside the database and it's not in the application. So the application needs to access the database a second time to retrieve the primary key that was just assigned. Some databases have special means to do this in one lookup, but anyway, they are proprietary, non-standard extensions of the SQL standard. So you become very dependent on a specific database if you use those. Another way is to have a table in which the application itself keeps track of primary keys, and there are quite sophisticated algorithms out there called high-low which work in a cluster, which means they work when different applications access the same database, and one access to this primary key storage table retrieves a whole bunch, a range of numbers, and that can afterwards be assigned by the application. There are tricky issues. For example, what happens if different kinds of applications access the database? They all need to use the same strategy to assign primary key values to newly inserted rows. Another issue to keep in mind is if you replicate the database, you need to make sure that both sides of the replication have compatible, ideally identical, ranges for the primary keys, so that there will not be mismatched. So that you won't run into the problem that one database assigns a primary key value that was already assigned by the other one. Those are things to keep in mind if you decide on a primary key strategy.
Okay, so now I have primary keys. How can I use these primary keys to make sure that I can reference another element from another table?
You're talking about foreign keys now. Those are just arbitrary columns that are in other tables and want to, sort of join these two tables together. Actually, they're not really keys. They're just normal columns. Let's get back to this example of persons and addresses. A typical way to do this would be to add a person ID column to the address table and store the primary key of a person in this person ID column of the address table, so that when you take a look at the address, you know which person this address belongs to. You can do this without using the database feature of a foreign key, and there are reasons to actually not use this foreign key feature because it has a little performance impact. Mainframe applications tend to switch this off for production. If you use the foreign key feature of the database, you have the additional benefit of having the database check consistency. That is, the database ensures that the value in the foreign key column is an actually existing value in the primary key column of the referenced table.
Which leads us nicely to constraints.
Oh yeah, good point. This is just one example of the constraints that databases support. The most general kind of constraint is you can have arbitrary Boolean expressions on the contents of a table as a constraint. They're called check constraints, and they're part of the SQL standard. It's one of the rarely used features. Few developers know this or use this. And the benefit is that you have a self-documenting database schema. And, obviously the database is sort of like designed by contract. The database checks at runtime if what the application gives it is valid. This is, of course, no replacement for checking in the application as well, because the application should only attempt to insert valid data, but the database makes sure that only valid data gets into the database, and it's sort of a catch-all. It's sort of like a second lock on the vault to make sure data integrity is maintained. This is what's behind these constraints. They are enforced at runtime while the application tries to write into the database, and if the application tries to write data into the database that violates this constraint, an exception is thrown, or anyway, the database returns an error, and most importantly, does not insert the data into the database or update the data. A special case of this constraint is not null, which is probably the constraint most developers are familiar with. It just means that a particular column must not be null, and There's another concept in databases, which is also not part of the standard, but it's quite widely used and useful. That is triggers. And it's different from constraints. Constraints are a condition that is checked, and if it's violated, the modification is rejected. Whereas triggers are code that is executed in the database and that is triggered by some kind of change. So for example, you can have a change after a row was inserted. You can have some stored procedure, we'll get to those later, that is executed whenever data was modified. You can perform some kinds of constraint checks there, but they are more powerful. The downside is they're not standardized.
I guess that's it for the relational paradigm. Now let's have a look to performance. What kind of performance aspects do we have in relational databases?
Okay, yeah, well, that's a huge topic. As I mentioned, the relational paradigm means that you do not have a single starting point and you do not have predefined paths through the database. So whenever you look up a row in a single column, you have some kind of where clause, so you have some kind of condition and retrieve only those rows that are met by this condition. Which means that naively implemented, the database engine would have to go through every row in the table and check the condition. And then doing this, collect all those for which meet the condition. This is called a full table scan, and it's obviously really, really bad.
Really expensive.
It's sort of the worst case in terms of performance, because the database must read all the data of the entire table from the disk and look at it. So what you can do is create indexes, which means give the database hints, or tell the database to create a cache, sort of a mapping between certain values in a condition and the rows that meet these criteria. The simplest index is an index on a single column, typically the primary key. So that if you say, I want to have the row of the person table with a person ID 5, the database will not have to go through the entire table, but it has a lookup table that starts with the that is sorted by the primary key, and it looks up where on the disk the row with the ID 5 is stored, and then retrieves this. There's a whole science behind much research going into how to implement these efficiently. The key idea behind implementations today is trees. Ideally, databases will want to keep these indexes in memory, which makes lookup very fast. But for big databases, it's not possible to keep these indexes in memory. And the second best thing is to have some kind of binary tree, some kind of easily indexable structure, which on disk, which makes it fast to look up on disk. You can have indexes that span several columns. Those are much more specific in their usefulness than single column indexes, because they are only helpful if you have queries that have exactly this combination of columns in their where clause.
Can you give an example on that?
Well, let's say we want persons with an income in the range of between $30,000 and $40,000 a year, and we want to have those with the job title of manager. Then we would have a select clause in which the income column and the job title column are part of the where clause, and the database, without an index, the database would have to scan the entire person table to retrieve all the employees that meet criteria in those two columns. But if we have an index for these two columns, then in combination, then the database can use this combined index to retrieve only rows that match the criteria without going through the entire table. It's much faster.
Okay.
These things can become really, really complicated if you have inner selects and complicated joins. And the best approach to this kind of performance tuning, because, indexes are performance tuning, is to write an application with few indexes in the beginning and then do measurements. Find out what kind of queries take up most of the time and then find out why. Finding out what kind of queries take up most of the time is just normal profiling. Databases have tools for that. You can even do that in the middle tier if you want to, because in the middle tier you know what kind of queries goes out and can measure that. But finding out what takes up the time is more tricky. And in order to understand that, database products have tools that provide you with what is called a query plan. A query plan is, let me start a different point. If you send a query to the database engine parses this query and tries to optimize it, tries to turn it around this way and that to make the best use it can of indexes. There are many different ways of approaching this. It's often a good idea to first throw away most of the data. If you have two conditions, one of them throws away most of the data, another lets in most of the data. It's a good idea to first throw away most of the data and then look at these small resulting set and then go through that a second time. There are all kinds of different tricks, and there's much research going into that. And after this is called the optimizer step, and the output of the optimizer is the query plan. The optimizer, the query plan tells the database to do a full table scan on this table and use this index on another table, and so it spells out the details of how the database accesses data, and it's obviously this is very specific. The tooling and the things the database does are very specific to the different products, but it's definitely worth looking at in the documentation of the database engine to get an understanding of this and play around with it a little, because that's the approach to getting efficient database applications, to tuning the database, because only if you understand where the performance is spent, you know which indexes are useful. Otherwise, you'll end up with lots of indexes and still most of them won't be used, and you'll still have some gaps. So analyzing the performance by looking at the query plans is the way to go.
I also heard that you can even run into deadlocks with indexes. Do you want to say something about that?
Yeah, there's a story behind that. In a project I once was, there were very many indexes on a database. I'm not going to tell you which product it is because it might reflect badly on this, and it might happen with other products as well. But the indexes are stored in tables internally in this database product. And when a row was inserted or modified in a table, all the indexes need to be updated. And this led to a situation, an exotic situation, but still there it was, where concurrent modifications to the table caused a deadlock in the updates to the index tables, which meant that performance went extremely down the hill, sometimes erratically. We figured that out looking at the query plans and the internal logs of the database. So having too many indexes will degrade performance even without deadlocks, but deadlocks in the index tables are sort of the worst case for that.
When optimizing a database, there are two different things you can optimize for. Do you want to tell us something about that?
Yeah, good point. There are basically two different kinds of things you do with databases, many applications. One thing is putting data into it and occasionally retrieving data. And the other is running huge reports on it, only reading, and putting much load on the database reading it. The first thing is called OLTP, Online Transactional Processing. And this is sort of what you think of if you have an interactive application, like you log into Amazon. Then the books are probably stored in a database. I don't know, but I'd expect them to be. And so you, when you do a query, the books are restored and the details are retrieved from the database, and your cart is probably stored in the database somewhere. If you order something, it's stored in the database. It's sort of single row insert and very low scale retrieval. But oftentimes in the back office, you have very, very different kinds of things. They will run huge reports on how many customers bought what kinds of books today, to optimize their advertising or to create a prognosis for the revenue, that kind of thing, which does huge queries over millions of rows in the database. And those two they require very different tuning in the database because they want very different optimizations. Online transactional processing, you will need few indexes. Most of the time data is stored, and storing the data quickly is very important. But quick response times, deterministic quick response times are very important. Whereas in this back office part with the huge queries, that's called OLAP, online analytical processing. It's related to data warehousing. There you have huge queries for huge reports that might run several minutes and, well, basically bring the database server into saturation during that time, which means this one query takes up 100% of the resource of the database server while it is running. You don't want to have that kind of impact on the while people are working with Amazon, want to buy books and then cannot buy the books because one of those reports is running. And you also have very different kinds of indexes that you want there, very specialized for those kinds of reports.
So typically you end up with two replicated databases. One is optimized for read performance and another one is optimized for write performance if you need that, right?
Yes, exactly. That's one typical architectural approach, to have two databases, one for the for OLTP, one for OLAP, and then have database replication from the OLTP into the OLAP or the data warehouse, typically during nighttime or low load hours if you have those.
So another huge topic, I guess, is security. So what can I do in my database to ensure certain security things?
Oh, security is, as always, a big topic. First of all, well, the different parts of security. One is taking care to making it difficult for people who work for your own company to spy out data. The database administrators, people working in the data center, because typically data is exchanged between the application and the database in a non-encrypted format, which is usually not an issue if it's inside the data center. You have secure network lines. It is, however, an issue if you have, or potentially an issue if you have data running. If you access the database from outside the data center or even over the internet, that's usually not a good idea because the data goes unencrypted and passwords may go clear text. For that, it is a better idea to have three-tier architecture with an application server running in the data center and having a secure network between the application server and the database. This is sort of the raw wire espionage thing, which is good to keep in mind, but is not such a big issue in practice most of the time. At another level, it's important to fine-tune or to manage who may access which data in the database or modify what data in the database. You want to provide different users with different permissions on the database. And for that, databases come with user managements of their own. And it's quite sophisticated usually. The database servers support users, they have user groups even, and you can assign them rights, saying this user may, or everyone in this group may insert data into the person table, or may read data from the person table, but or you can even be more fine-grained by saying can read all columns in the person table except for the income column, which is confidential. Or some databases even have data-driven authorization by specifying a database user can read data from the employee table for all those rows with an income of less than $30,000 a year, or for employees whose job title is not manager. This is quite fine-grained, and it's good as far as it goes, but it's not widely used nowadays for many applications. I'll go into that right away. There's a different model now, and that is the model of having. This first approach is basically having one database user per human user of the system. So you have administration of the users and the permissions in the database. And if I log into the application with my name Arno and a password, these are passed through to the database, and the application logs into the database using the credentials I provided at login. This has the benefit of that it permits traceability and logging in the database, and this is sort of the traditional approach for which databases are optimized. Another approach is to have an application server in between and provide a technical user, or have the database provide a technical user, a generic user, to the application server, and all access goes through this one generic user. And all the permission checking is done in the application server, which means that as long as the application server is not compromised, there's no problem, and the entire responsibility lies with the application server. The downside of this is that you have no traceability in the database. Who accessed what? All this logging is not useful anymore. The upside is that you can have things like connection pools in the application server, which means that creating a connection to the database is an important thing, expensive thing, and a connection costs lots of resources, and it takes some time to create. So application servers create a pool of database connections in advance and pool that, and whenever someone needs one, it's returned from this pool. And when its transaction is finished, basically it goes back to the pool, which means you need fewer transactions, you need fewer connections at the same time. Another benefit is that you have better integrations with single sign-on systems, and you can have, applications nowadays need to know about permissions anyway, so it's not sufficient to have the permissions in the database. You need to have them in the application server anyway to gray out menu items or whatever in the user interface.
Another huge problem in these kinds of systems might be SQL injection. Do you want to tell us something about that?
SQL injection is based on the way many applications are implemented today by using string concatenation to create their SQL on the fly. One example, let's say someone logs in and you have a select statement to check authorization by things like select asterisk from user, where user ID or where username equals quote the name that was entered in the login dialog, quote, and password equals quote, and then the password that was entered in the login dialog, and then you add another quote and send it to the database. And if you find a row, then you know that the user is permitted to access the system. If you don't find a row, you know the login was invalid. Now, if you enter quote or 1 equals 1 or quote equals quote into the password field, then this leads to another valid SQL statement, but this SQL statement basically accesses any account, because in the where clause you have 1 equals 1. So SQL injection is based on entering SQL code in the user interface, and if the application is programmed insecurely by using string concatenation in an unsafe way to create the where clauses, then the application can be compromised. There are ways around this. Many libraries nowadays are intrinsically secure against that. Prepared statements in Java, for example, are safe against this. But still, it's good to keep in mind.
That's all for security now. So now let's maybe have a look for the different database tools.
Okay, I'll be quite brief here. There's a wide range of database products out there, and you can look at the data sheets of the vendors if you want to compare them. And anyway, in many companies, there is one global decision for one database tool. Anyway, the SQL standard is what is common to all of them. They all implement the SQL standard to different degree, but quite widely by now. They have their specific enhancements of the SQL standard that add on certain special syntax. It's used to be important. It's not that important anymore to have these syntactic add-ons. But what is really, really important, and is usually the key thing to making the decision, is the administration tools around the database. For example, user administration, table space administration, or performance tuning support, replication support, but also support for doing hot backups. That is, making a backup of the database while it is still in use without compromising the consistency of the backup. Running all kinds of diagnostics, that kind of thing is very important in enterprises, and those things are really what differentiates commercial products from open source products much of the time. And this is where the commercial products have different specialties. So that's one important thing to look at. Another thing is scalability. How fast is the database out of the box, which is interesting. Where it is interesting to notice that, for example, MySQL is very fast compared to much of the bigger databases, especially if you have mainly have read access. So this is something to really take a look at. But then another thing is to look at how well this performance scales up. If you have a database of a terabyte, it's a very different issue from fast performance for small databases. Support for clustering, having several databases that act as a single database, is another thing that goes into this performance and cluster and scalability thing. And then all these operational things, like replication, having high availability support, and service level agreements that support these. But then you also have special features that may or may not be useful for your application. Many databases now have some kind of XML query support. That is, they can return data as XML. They have custom types, custom objects. They have stored procedures. Stored procedures, yeah. There's a lot of debate going on around stored procedures. Some purists say they're not part of the standard, you shouldn't use them. And anyway, if you're a Java programmer or a C# programmer, you're not very much in touch with them much of the time. You can do anything in Java or in C#.
So what are stored procedures?
Good point. Stored procedures are procedures that are stored inside the database in some kind of proprietary language, PL/SQL for Oracle, for example. And this code is executed inside the database. And stored procedures basically move program logic into the database, which is bad for things like refactoring, for maintainability, that kind of thing, but it's very good for performance. This is basically the trade-off behind stored procedures, and if you need them, you'll know that.
And I'm basically calling a stored procedure from an SQL query.
Yes, well, the syntax is not standardized. Different databases have different dialects, different syntax for calling the stored procedures. But yes, basically you call it from SQL or via an API. Those are the two approaches that are there.
So now we heard how databases are implemented in general. How would I make use of them in my actual system?
Yeah, well, this sort of drives at the architectural issues. It is a wide area. I'll just start by talking about the things that come to my mind. First of all, there is object relational mappers. They are basically libraries or frameworks that make it easier to get objects and all the object-specific way of thinking, like references, collections, maps, inheritance, into a relational database that has none of these things, and retrieve data from a relational database into these kind of object things. We're going to have a dedicated episode on object relational mapping, so I'll not go into those very much here. But if you start thinking about the system architecture with a database, the first thing to keep in mind really is the different roles of people who deal with the database. There are at least 4 roles, 4 different kinds of people who deal with the database in a development effort. The first role is the users of the database, that is, the programmers. Those are usually the first that come to our mind. The people who write the queries, who write the modification code, who write the update, the insert statements, who call the stored procedures, who write the stored procedures, all that kind of thing. This is basically using the database. It's very important, obviously, but it's not the only role. At the other end of the spectrum is the database administrator. He's the guy who takes care of how many disks in what kind of RAID arrays are available, how fast data in the database grows, and well, he's the guy who orders new disk arrays if the old disk arrays tend to become full. He's the guy who monitors performance, all that kind of thing. A whole different approach, whole different view onto the database, and it's a good idea to talk to the system, to the database administrators, to the system administrators next time you develop a database system. It'll open your eyes and you'll get a whole different view, and it's important to, well, it's a good idea to have the database administrator's perspective in mind if you write a system that uses a database. And sort of in between, there's the database design. That is, the people who decide what tables, what columns there are, what they are called, what relations there are between them. That's the logical database design. And there's the physical database design, which is again distinct from that, which is how are the tables spread across different table spaces. For example, if you have a huge application in which data runs all the time, many rows a day, let's say a couple of million rows every day, and the most frequently used data is the data that of the current day. Then it may be a good idea to put the data to split the table physically, which can be transparent to the application, but to split the table onto two table spaces based on a timestamp value, and have the data that is of the current day in one table and older data in another table, that kind of thing. That's physical database design. So those are the four roles of people who deal with the database.
Wouldn't I use views in that case? Materialized views?
You might want to use a materialized view. Depends on what kind of queries you have. Splitting data on different table spaces that are on different hard disks can be a significant speed up in many situations. A lot better than having a materialized view that is in the same table space on the same disk. Again, depending on the situation, one or the other may be the better approach. I was just sort of trying to illustrate the range of things you can do at the physical level if you have huge amounts of data and want to optimize for that.
So you mentioned table space now. What is the table space?
Table space is, well, it's the disk space on which a table is stored, basically. It's specific for different vendors how they manage this. Basically, every table, or well, every row at least, is on one table space. Typically, every table is in one table space, and managing table spaces, predicting the size of the table spaces that is needed, and maybe even optimizing so they can be put on different disks. So the performance of the disks is added and increases overall performance. That's the kind of thing you can do by dealing with table spaces. The naive approach that most systems take, at least in the beginning, is to have the entire schema on one table space, and that's that. So most systems do not really actively do any physical database design to optimize performance. Another thing that is related to using different table spaces is distributing the database itself using clusters. Again, there are trade-offs there. First of all, price, of course, but leaving that aside, if you have a cluster, the key idea is that the performance should go up. But if you have a cluster, that means that you have distributed locks, because the database must still maintain integrity across the entire cluster. Depending on the specialties of the product, it's important to look at the trade-offs that are involved, but planning to cluster the database is one way to improve performance. It's definitely an architectural issue. It's something to look at, maybe even early on, because may require some effort, some rework in the database design. Again, as with any optimization, you should do that only after measuring the performance.
And obviously it should be part of the decision-making process, as some of the databases do support clustering and others don't.
Oh yes, of course. Yeah, I was assuming if for an enterprise application you were using an enterprise scale database system anyway, and they do support clustering. But yes, of course, this is an important part of the decision making. Yes. Another thing I mentioned that already is the replication thing, OLAP versus OLTP, or more generally for different kinds of of uses for the data, it may be a good idea to isolate the performance hits by replicating, especially if there is little load during the night. You always have that kind of thing available. Getting closer to the code you write, there's the decision between having a 3-tier and a 2-tier application. 3-tier is what's usually done, so it's the modern way of doing things. It's the way we do things here, which means you have a server-side application server that runs in the data center, and all user management, authorization management is in the application server, and only the application server talks to the database. It's sort of more secure because you can put the application server in a demilitarized zone, have a firewall between the application server and the database, which makes it harder to hack the database server. And the 2-tier approach, on the other hand, means that you have logic in the client and also logic in stored procedures stored in the database, and the client application talks directly to the database, which means you have a rich client, not a web client, which is, well, sort of against the trend. Still, there are very important applications that or class of applications that use 2-tier architectures. For example, call center applications where where fractions of a second in response time are very important. You have few users, you have a controlled environment, that kind of thing. 2-tier architecture can be a very good idea. Then going even closer to, even more towards the code, it's a good idea to know the details of the access library you use to access the database. You have some kind of result set you iterate over, but databases nowadays support scrolling in both directions, usually using things called cursors, and you can write data to the cursor directly. That kind of thing is good to know to know what you can do. And one final thing about the architecture is one of my favorites, internationalization.
Why is it a topic in the database design?
It's important because using different encodings has an impact on the number of bytes that every character needs to represent it. As long as you use one of the ISO character sets, ISO 8859.1 or whatever, you're on the safe side. You have one character or 1 byte per character, so it's sort of intuitive. But obviously there are limitations with regards to internationalization. You cannot have Cyrillic or even Chinese characters in there. So if you want to go to UTF, well, if you use UTF-16, you have 2 bytes per character, and the sizing of the database columns is typically in bytes, not in characters. Very tricky. From the database perspective, it's sort of obvious because the database needs to reserve some amount of memory, and that's in bytes. But if you use UTF-16, you need to make all your varchar columns twice the size. Or if you use UTF-8, which is a variable length encoding, for 7-bit ASCII, you have 1 byte per character. But if you have umlauts, you have 2 bytes per character, and for more exotic characters, you have up to 6 bytes per character. So if you if you're planning for an internationalized application, it's important to think upfront what kinds of characters you want to support, how do you plan to size your database columns, and then you need to size them accordingly, and then only after you did that, you should actually set up the database to use the encoding you chose. It's very tricky, and oftentimes is not noticed until late in the cycle because it's non-obvious. Even during testing, you would need to test the database with Cyrillic strings of big size, which may or may not be a test case depending on the technical expertise of the people writing the test cases.
Okay, so I guess we're done, right?
Yes, I think we basically covered most things. There is, however, one story I would like to share with our listeners, which is my favorite database driver bug. And again, I'm not going to tell you what kind of product it was, because these kind of bugs are present for many different products. This product is not worse than all of the others, but it's one of the really big players in the game. So there was this this application I was writing under huge time pressure, and it started behaving weird. So I spent 2 days, I think it was, debugging the database driver until I found that if you used Java prepared statements using a batched update and had a database table that had 2 big decimals and one varchar. No, it was 2 varchar columns and 1 big decimal column, I think. And if you did in the batch update, you did 2 updates using specific strings. Then for the 3rd update, the upper limit of the big decimal column went down to less than 100, regardless of the constraints you actually had stored in the database. And all these conditions actually needed to be present for the bug to turn up. It was really weird. Well, after I found it, it was easy to work around it. The reason I'm telling you this is, don't take anything for granted. Databases are there. Databases are very, very reliable. They're excellent products, and it's good to rely on them. But if there is a problem, think out of the box. The database may be part of the problem. Even the database driver may be part of the problem. And this kind of mindset has helped me in lots of projects.
Okay, so do we want to do a short wrap-up?
Let me see. Databases are cool. Databases are here. They're here to stay. Databases are very, very useful. And despite what I said, they are often the best trade-off for a way to store data. Why are they so predominant? I think one of the key things is there is a very, very well understood and well standardized standard for the SQL language. They're sort of interoperable. Well, no, not the databases are interoperable, but if you know SQL, you can deal with any of the databases. They're more or less interchangeable from the developer's perspective. They're very mature technology. You have special solutions for many special problems like stored procedures, like replication. You have very good administration tools. Obviously, they are very widely used, which makes it sort of self-perpetuating because they are widely used. That means they are further developed. They are well known. The money goes there, etc. That's why they sort of keep being used. And, well, to be honest, they are extremely well optimized by now. So basically, they are pretty fast. Faster than anything you can write anyway, at least in one of the typical development projects.
Okay, so thanks, Arno.
Thanks, Bernd. It was a pleasure talking to you about databases.
Bye-bye.
Bye.
Thanks for listening to Software Engineering Radio. If you want more information about the podcast and all the other episodes, visit our website at se-radio.net. If you want to support us, you can donate to the SE Radio team via the website, or you can advertise for SE Radio, for example, by clicking on the Dig, Reddit, Delicious and Slashdot buttons. To contact the team, please send email to team@seradio.net, or if it's specific to an episode, please use the comments facility on the website so other people can read and react to your comments. This episode of Software Engineering Radio, as well as all other episodes, are licensed under a Creative Commons license. Please see the website for details. Thanks to Charlie Crow and the Podsafe Music Network for the music used in this show. The song is called Vegas Hard Rock Shuffle.